Thank you. All right, so I'm going to present you our plan for global instruction selection. But before I start, I'd like to emphasize that this presentation focuses on the prototype that we want to develop on open source. This prototype will be the backbone of the new instruction selector. So really what you want to remember here is that it's a proposal. Some of the points of this proposal have not been discussed yet on open source, and they may be controversial. And this is fine. What we want with this talk is to invite you to have a conversation with us on what is the best way to move forward with this new instruction selector. And with that, I will start with a definition. So what is instruction selection? For the purpose of the presentation, I'll go with a simple definition. So instruction selection is the translation from target independent intermediate representation, or IR, to target-specific IR. So to put that into LLVM terms, it means translating from LLVM IR to machine inster. Let's see what we have right now as the instruction selector framework. So what we have is called SelectionDAG, or SDISel. DAG stands for Directed Acyclic Graph. Let me go a bit into detail on how that selector works. So basically, it's a path, which is represented by this white box, that takes LLVM IR and produces machine inster. But to get there, we are going through a bunch of phases. So first of all, SelectionDAG builds a new representation that is named SelectionDAG node. So here on this picture, the terms in bold are intermediate representation, and the other terms are phases in the path. So with this new representation, we go through optimization that are named DAG combine, that basically do some canonicalization and people optimization on the representation. Then we go through the many passes, the many phases of the legalization, which basically translate anything that can be represented on the LLVM IR into what is supported for the actual target. After that, we have another phase of optimization. Then we select these nodes into target-specific nodes, but we are not done yet. Since we are representing DAG, so graphs, we need to linearize those graphs to be able to produce the sequential representation that is used in machine inster. So we have to schedule those graphs. And finally, we have our machine inster representation. So as you can see, it's a lot of work to do the instruction selection. And in fact, it's even worse because we have to do that for every basic block. So in the past, that's why we introduced another scheme within this instruction selector framework that is called FastISL. FastISL is basically a direct translation from LLVM IR to machine inster. However, to be able to be fast, we have to compromise on what we can support as input from LLVM IR. And this is, we have a different coverage of what is supported for LLVM IR for each different target. And what this means is that FastISL may fail. And when it fails, you need to fall back on the existing SelectionDAG and heavy framework. So basically, we have two paths within one instruction selector framework. One path that is named the good path because it generates good code that has good runtime performances, and the fast path because the goal here is just to generate code as fast as possible, and we don't care that much about the runtime performance. And from the target perspective, what it can do is just drive those schemes through hooks, and that's about what control it has. So to summarize, with the current instruction selector framework, we are going from LLVM IR to possibly SelectionDAG node and then to machine inster. as you can imagine, this has a lot of problems. First, it's a basic block scope. So like I said, you have to do this selection for each basic block. So that means that you have a very narrow scope of what you can see. And basically, each time you want to take global decision on, let's say you want to optimize the selection for your addressing mode, for your target, the thing is that you may not see all the uses of the addressing mode you want to expose or the definition. And so basically, you cannot make this optimization in that framework. So because of that, we came up with other LLVM IR passes that helps to work around these problems. So like we have a pass named CodeGenPrepare that's basically the only purpose is to push instruction within basic blocks, so duplicating instruction into the same basic block so that you expose this optimization opportunity to the instruction selection framework. And similarly, you have the ConstantHoisting pass that put together constant that can be reused between different blocks, because this cannot be done during the instruction selector framework. But the problem here is that not all the constants are exposed, because some may happen during the instruction selection. So basically, these new passes have their own problems and their own limitation. Another problem is that we have yet another representation to do optimization, this SelectionDAG node representation. And this means that you have to create this representation and get rid of it. So you have a peak in memory usage, and it's also an overhead. And finally, this is a monolithic transformation. So like I previously showed you, basically the target cannot do anything about the pipeline of the instruction selector. It has to drive it through the few targets hook we have, but that's about it. If you want to do something right before legalization, you can't. If you want to do something right after legalization, you can't either. So you're basically screwed as you're basically stuck as before the instruction selector or after. You cannot work within the instruction selector. All right, so let's see what would be the goal for a new instruction selector. So first, we want a selector that is global, so to solve the problem I mentioned. So we want to have a scope that is at the function level. We want something fast, obviously. And also, we would want something where the fast and good path are a shared code path, and not two different code paths that we will have to improve for the different goals you want, or fix bugs at two different places. We want also an IR that represents ISA concepts better. We want a more flexible pipeline, like I said. You want to be able to do your own target-specific things within the instruction selector pipeline. We want an easier to maintain and understand framework, especially if you think about legalization, and if you're familiar with how that works, it's kind of hard to get it right. Would be nice also to have a self-contained representation, because right now, when we do the instruction selection, or to some extent on machine inster as well, we have still some backlinks to the LLVM IR. And it would be nice to be able to cut those backlinks so that we can really focus on the representation we are generating code for, and not have this LLVM IR that is here just for the purpose of those backlinks, and we can get rid of it to get rid of the memory that it uses. And of course, we don't want to change LLVM IR. So like I said, this is what I'm going to present here. It's a prototype. So although there are a lot of cool things we would like to do for this new selector, there are some things that we won't have time to do. And one of them is the reuse of ins_combine. So ins_combine is an optimization that happened on LLVM IR. And this optimization has a lot of code that looks similar to what we do in DAG combine. And it's likely that if we create a new scheme for the instruction selector, we would have to replicate again this logic for the new scheme. And it would be nice to have tools to refactor this logic and be able to target this different level of intermediate representation. Although we think it's very interesting to do, it's not something we would do for the prototype timeframe. And actually, we believe that this could already be started right away for some people that are interested in that problem. Likewise, we won't look into improving table gen. It has been several years now that we are talking about the next generation of table gen. Although I would like to work on that and improve it, we won't do that for the prototype for the exact same reason of the reuse of ins combine. And finally, although we want the new instruction selector to support all the crazy target-specific features that you may think about, at this point, we want you to make sure that the framework will allow you to make this target-specific feature to happen, but we won't actively work at supporting them during the prototype timeframe. All right, so now that all that is settled, why not fix SelectionDAG? It has been here for a decade already, so looks like a pretty good framework. So what shouldn't we just keep using it and just fixing it? So first of all, there are some hard limitations on the underlying representation. So like I said, SelectionDAG is based on directed acyclic graph. So this means that any time that your program has a loop, it may create a cycle within the representation. And you can't represent that on a DAG, otherwise it's not a DAG anymore. So one can say, OK, we can do some clever tricks with fees or memory dependencies so that we know where those cycles are and we just don't care. All right, that may work, but that sounds error-prone. Anyway, let's say for the purpose of the presentation that we do such acts. Now, if you think about the SelectionDAG framework and you want to break it into pieces so that the target has more control of what happens, it means that the optimizer that would be target-specific that will be inserted into this pipeline would need to work on this SelectionDAG node representation. So that means that you would introduce yet another intermediate representation, the SelectionDAG node representation, to optimizer. So that means that now you will have 3 different intermediate representations that you will have to choose for where you should put your optimization. So the LLVM IR, the machine inster, and the SelectionDAG node. That doesn't seem compatible with the make it easier to maintain and understand. Also, we think, and FastISL is a proof of concept of that, but SelectionDAG node IR can completely be avoided, and you can go directly from LLVM IR to machine inster. And finally, like I previously briefly explained, there are some inherent overhead due to this representation. So you have to build the DAG. Even if you don't have to do anything to do the translation, you still have to build the DAG, schedule the DAG to produce the sequential order, and then translate the nodes into machine inster. And this is not compatible with FAST. All right, so let's introduce a new framework that we call global-isel. At this point of the presentation, I'm going to build the pipeline of this new framework. And I'm going to go step by step. So first, we start from the LLVM IR. This LLVM IR goes into a new path, what we call the IRTranslator. So I will explain how the IRTranslator will work on an example. So here you have this LLVM IR representation, which basically takes a double and a pointer on a double. It loads the value from the pointer to a AND bitwise on it with the other value and returns the result. So what would be the role of the IRTranslator here? Basically, you would have to translate the LLVM IR to machine inster with some generic opcode. So it shouldn't be a surprise that we are looking at machine inster here. It's already the representation that we use for the backend. And since it's that representation that we use, it's known. And also, it's well suited to represent the ISA concepts. So let's see how this translation would work step by step. So we start with the function, and we create a machine function out of it. Then comes the arguments of the function. So at this point, this is the ABI boundary. So let's say for now that we don't care about ABI boundaries, and we just have two virtual register, two definitions of virtual register that are available. We move to the next instruction. This is a bitcast. For machine inster purposes, bitcasts are just NOP. So basically, we don't need to translate that to anything. So what this means is that one IR instruction can map to 0 or many generic machine inster. Then we go to the load, and this, as you could expect, generates a generic load that is represented by this GLD opcode. For those that are familiar with machine inster, you know that the type of the operand on result of a machine instruction is encoded within the opcode. So it means that if you have an 8-bit load, you would have a LDI8, and if you have a 16-bit load, you would have a LDI16. But here we represented all what that LLVM IR can cover, so which is basically anything that you could represent with extended value type, and this set is infinite. So it won't scale to create an opcode for each possible type. So what we do instead, we put a type on the machine inster. So this example is not well chosen in the sense that for loads, the type is not that relevant. What's really interesting is the size, but you get the idea. Basically, you have a type on the machine inster. Okay, but also if you're familiar with machine inster, you know that virtual registers are mapped to register class. But at this point, we don't even know what target we are looking at. So we don't know what register class are available. And even worse, maybe this type cannot fit in any register class. So what do we do about it? Well, we record the size of the virtual register. It's basically just what we need. Virtual registers are carried bits around the place, and what defines its type is just the uses or the definition of the machine inster. So let me fill in the blanks for the previous definitions. Let's say we are targeting a 32-bit architecture. So you have the double value is 64 bits, and you have the address that is 32-bit because pointer is 32-bit on this target. All right. So now you go to the bitcast. It's a NOP again, nothing. And then you move to the AND, and you get what you would expect, a generic AND with the two input value and definition. And you move to the bitcast. Again, for machine inster, it's the NOP. And then you end up at the ABI boundary. So at this point, you have the core representation of the function. But we believe that it's important to expose the ABI as early as possible so that the following optimizer are aware of that would be emitted and can work on that. And in fact, it's not new. It's already what we do in the SelectionDAG builder. We do the ABI lowering. So let's say here that we target some ARM chip. The 64-bit value is passed through two 32-bit registers. And basically, at this point, what you have to do is take those two registers and put them together to create a 64-bit value. And this is done with this vmove DRR operation. which produce a FPR register. So what's interested here, so don't look at the ARM-specific instruction. It's basically a fancy move to create a big value from two small values. So what's interesting here is that the virtual register can be assigned register class like it's always the case. So this does not change. It's compatible. It's just an additional information that we carry. The next parameter is passed through R2, so it's just a copy. And then the result is copied from a 64-bit value into this 32-bit register, and then you return with the ARM-specific value. So again, at this point, the target can just insert its own opcode. There's no crazy layering going on where you need to create some special SelectionDAG node to be able to represent that. And that's it for the IRTranslator. So what we saw is that we translate the LVM IR to some machine inster with generic opcode. So the G is in parentheses because it means that at this point you have generic opcode, but you also have target-specific opcode. Then goes the Legalizer. Before I dive into it, I would like to emphasize that this pass is controversial. Where the legalization needs to happen and how is something that needs to be discussed. But for the purpose of the presentation, we want to give the whole picture of how we think it would be, it would work on the machine inster framework. All right, so the Legalizer starts with the output of the IRTranslator. There's something new with the legalization process here. There's no illegal types per se. There's only illegal operation. And as you can imagine, the role of the Legalizer is to translate this illegal machine inster to legal machine inster. So let's see how it works. You start with this AND. So on ARM, 64-bit AND are not supported. So you have to expand this AND into two 32-bit AND. So this is something we already do in the existing legalization framework. What's new here is that if you look at the highlighted region, the input value and the output values are the same. So on the left, you have val and loaded as input. On the right, you have val and loaded as input. On the left, you have AND as output. On the right, you have AND as output. So basically, with this new instruction, extract and build sequence, extract are about extracting different value from a bigger value, and build sequence is about build sequence concatenates value together to produce a bigger value. We are able to express the state of the directly in the IR. So it's something new because previously the state of the legalization was kept into a global structure within the SelectionDAG framework. So what this means is that if you look at the representation before this one-step legalization, this is valid machine inster. If you look on the right after one-step legalization, this is also valid machine inster. So it means that you can just do one step of legalization and it's still valid. It's very easy to understand, and we believe it would be easier to debug and work with it. Like the existing legalization process, it's iterative. It applies a set of transformation, and we iterate until no more changes. So just to go through the whole process, we now have just those three instructions that are not legal, so you have to legalize it into this fancy copy operation that ARM supports. So what's interesting here is that if you think about it, this looks similar to what we've done for the ABI lowering when we did this put two values together So we believe that it would be nice to have some kind of legalizer toolkit to be able to do some custom lowering for legalization. And I will explain how we can use this toolkit later in the talk. All right, that was legalization. Next comes the RegBankSelect. So this is something completely new compared to the existing framework. What's about it? So if you remember, at the beginning when we translate to machine inster, we recorded sizes for the virtual registers. But at some point, this virtual register needs to be assigned to register banks. And that's the purpose of this path. Assign virtual registers to a register bank. So a direct translation here would be, all right, you have the 64-bit value, you put them on the floating point register bank, and the 32-bit value, you put them on the general purpose register. And that's it. So you could think about that like, if this is a non-optimized build, you've done the mapping, so you're done. But you could do more fancy things like avoid cross-domain penalties, like going from integer to floating point. You could also be aware of register pressure and choose the bank based on if you're exceeding or not the register pressure on a bank. So let me illustrate this kind of optimization that we can do with this path. So let's imagine that RegBankSelect has access to some API where it can ask the target what register banks are supported for a given opcode. Let's start with the fancy copy opcode. So the target could say, I can create this definition on an FPR register that will set all the bits you are interested in. This is basically what this mask means, the 0xFFF. It's basically all the bits you are looking at would be in this specific register bank. And this has a cost 1. I can produce this value for a cost 1. But I can also produce this value into 2 different GPR. One with the high part of the value you're interested in, and one with the low part of the value you're interested in. And this is a cost 0, because basically what you can do is you can break this fancy copy into 2 generic copies that can be coalesced by the coalescer, and this become free. So now you look at the use of that value. Again, you can read that value from FPR with all the bits for cost 1, or read that value from 2 different GPR. So basically, if you push the analysis one step further and not just looking at the current definition, you see that for cost 0, you can produce the value on 2 GPR. And basically, this path would just rewrite that into copies in that case. So basically, what we just did is that we assigned register banks to avoid cross-register bank copies. And for instance, on some ARM architecture, those fancy copies are about 20 cycles. And if you think about it, what we just did is that we took a fancy copy of a 64-bit value, and we expanded it into 2 32-bit value. And this looks like legalization, right? So we may use this legalizer toolkit that I mentioned previously. I know it's kind of a stretch to think in these terms, but let me take another example. So here you have this 64-bit load that is then consumed by this fancy copy. And basically, with the proper cost model, what you can do is just use regular copy and create the value and load the value directly from 2 different I32 load. And if you look at this specific transformation, what you really did is just expand the load into 2 32-bit load. And this is definitely a transformation that the legalization does. And that would be nice to be able to reuse it. And we can do the same thing with the other fancy moves. And that's it for the register bank select. So then we move to the select path. So the select path is about getting rid of the generic opcode that may remain to generic target-specific opcode. So in that case, it's those 4 instructions. So that's new. What's new here is that since we are already on the machine inster representation, we can do an in-place morphing. So let's take this generic AND, for instance, and the selection process is just about changing the opcode. The interesting thing about it is that if you look at the machine inster representation on the left and the machine inster representation on the right, both representations are valid. So again, you can print it, you can run whatever path you want on it, and it's really easy to debug and work with it. Like this existing selection framework that would be based on a state machine, and it will iterate until everything is selected. Something that is not illustrated in this example, but that I wanted to mention, is that you would be able to do combines across basic blocks. And at this point, you're done. You have your machine inster with all your target-specific opcode, and that's the end of the instruction selection process. So we saw how to go from LLVM IR to machine inster by breaking this pipeline down to different passes. So let me give a summary now. So we believe that this pipeline is the backbone of the new instruction selector. But you can imagine, since that now it's a regular pipeline with the patch manager and everything, you can add some generic optimizer at this point, like this new global-isel combine, whatever you want, CSE, target-specific optimization. And you could do that anywhere in the existing pipeline. So what this means is that the target can now tune the pipeline for its needs. Also, the generic path would use hooks so that the target has some a way to drive what's happening. And like I mentioned, you have this Legalizer toolkit that can be used by any passes to do what the legalization does, like expanding something or scalarizing something. Legalization stuff, you get it. So let's see how this framework achieves our goal. So first, it works at the function scope. So it's global. Great, that's one. It breaks down the process into passes. So that means it's a more flexible pipeline. We believe it's easier to understand and maintain. And like I give you a glimpse with RegBankSelect, it's a shared code path for the fast and good path. So basically, the fast path is just a trimmed down version of the good path. And also, the level of analysis within each path can change if we want to go fast or if we want something good. Finally, we introduced new generic opcodes for machine inster. So we believe that this will be fast, as FastISL showed that this kind of translation are fast. Obviously, this is an IR that represents ISA concepts better. We don't make any change to LLVM IR. And it's almost a self-contained machine representation. On machine inster, we have still some backlink to the LLVM IR that we can work on fixing that. All right, so how do we get there? So first, we will rename the SelectionDAGIsel into Legacy ISL. No, just kidding. We start the prototyping by focusing our attention on the translation. We'll make sure that we are able to lower the ABI. And for the first iteration, we would put out a complex instruction like switches or landing pad. Then we would add some basic selector capabilities. So we would abort on illegal types, and we would do the selection in C++. It's basically, at this point, it's basically what is offered by FastISL. And also, we would have a simple bank selection. Then we would add some legalization capabilities. We would support scalar operations, but also some vector operations. Because in the prototype time frame, we want to be sure that we will be able to handle any of the crazy stuff that can happen during the legalization. And vectorization is one of these crazy things. And at this point, this should be the end of the prototyping. So basically, each step is about 3-4 months work. So that's basically in a year. All right, then what? We will productize on what we learned. So remember that the goal is to make this prototype on open source. So everybody would see this prototype going on and can test it for its own target. And we would have data to back up what we need to do to productize this framework. And at this point, we can discuss timeline to remove the existing SelectionDAG and the FastISL scheme. But there are also other things that we can remove. CodeGenPrepare and ConstantHoisting, for instance, should not be needed anymore. And we should be able to do better in the new framework because we are closer to the target and we don't have to make this crazy heuristic on guessing what the instruction selection is supposed to do. But there are other things that we can also remove at the machine install level, like the exact dependence fixer that's used currently for x86. This can be done now with the RegBankSelect. Basically, the RegBankSelect optimization is now a generalization of the exact dependence fixer. And there are also things in the people optimizer that wouldn't be needed anymore or that can be done elsewhere in the pipeline where it fits naturally. And maybe next year, I'll come back and present the status of what we've done for this year. Now, if you're interested into the motivation of this new global instruction selector, I invite you to read Jacob's initial proposal that you can find on the archive of the LLVM developer lists. And that concludes my talk. Thanks for your attention.
Okay, we have a few minutes of questions. Go ahead.
Hey, this is Sergey Lerin from Quick. Very good presentation, very interesting. The only thing I wish you would cover a little bit more on control flow representation. The specific question I had, can you handle predicates at that stage?
So you can definitely think about predicate at that stage in the sense that that would work exactly how that works on machine install. So if you are able currently in your backend to model predicate, you would be able to do the same thing on the machine, on the generic opcode. That may not be perfect, and it's something we may want to revisit. But basically, anything that you can do in the backend, you would be able to do it in this framework.
And the global scheduling, you didn't cover any angles on that.
Oh, that's the thing. With the machine install, we don't need any scheduling anymore because we're already producing the code for a sequentialized version of the representation directly to a new sequentialized version of the code. So the scheduling previously, so there's two things, in fact. There's the scheduling of the DAG to produce a linearized sequence to produce the basic block, so to get rid of the graph, basically, and this we don't need, obviously. And for the scheduling, like optimizing the code for a better schedule, this will work with the existing scheduler. So basically, anything that exists after the selection would still be used like the machine scheduler that exists.
if we get the same terminology. When I say global scheduling, I mean moving instructions between basic blocks.
Okay, yeah, that's something we do not plan to address within the prototype time frame. And basically, at this point, we think that you would just select the instruction where it is, and if you can improve the placement of the instruction, then this will be done later on, like with machine CSE or machine LLVM, this kind of thing.
Okay.
But that's something we may think about and add a generic optimizer for that. Thank you.
Thank you.
We have a question here.
Hi, I'm just wondering how much of the existing code will be able to be reused once we get past the prototype stage. So I'm thinking about the code in LegalizeDAG, DAG combine, and also the table gen code for writing the selection patterns. How much of that do you think we'll be able to reuse?
So that's a good question. And I think at the end of the prototype, we would definitely have a better answer to that. But basically, the thinking is that we could maybe reuse or have some tools to rewrite the existing table gen pattern into the new patterns, because it's just a matter of changing the name of a SelectionDAG node into a generic node. For FastISL, you could just reuse it, but that shouldn't be necessary. So yeah, basically, we were thinking that it should be possible to provide some kind of compatibility layer so that you can still use the existing path so that you have a smoother transition. But yeah, it's something we need to explore, and the prototype will be here to answer all those questions.
Okay, so I saw you have a register bank selection phase. The work is doing basically is doing some work for a transitional register allocator. Why don't you just leave that to the register allocation?
So right now, the register allocator is about, so to me at least, register allocation is about assigning virtual registers to physical registers and choosing which things to spill. Here it's a bit different. It's about changing the instruction so that you can move the thing from register bank to register bank. And I think if you start to mix that with the job of the register allocator, it gets very complicated. So you definitely want to do that before. But yeah, this is something we can discuss about.
So can we get rid of the legalizer? So when you go from the IR, could we just do the legalization right there? So do you want to split it for engineering reasons, of it's simpler, or is there any more fundamental issue?
What do you mean by getting rid of the legalizer? Because
I mean, not having a separate path, so you first translate and then you legalize. Couldn't you do it one shot?
Oh, well, I guess we can. The question is it easy to understand? And I think the answer is no. So of course, it's something we can discuss about, but I think it's better to separate the concerns. And what gets us currently in the SelectionDAG ISL is that the legalization is very complicated, in my opinion, and it's very hard to debug and this kind of thing. So if we mix that with the translation, I'm afraid we end up in the same situation.
I just wanted to say that I think being able to test the legalizer in isolation is going to be critical. And so even if we want to have some kind of iteration strategy, I think we at least want it to be separable for testing purposes, because right now testing the legalizer is madness.
So I think I'm going to take the last question because we're running out of time. 1 second.
Would it be possible to run RegBankSelect for the legalizer and just pick a register class even for legal types, and then it will work out later?
Well, that sounds kind of strange to me to do that, because if you have illegal types, no, if you have values that cannot fit a register bank, what do you do about the register bank select at this point? So for sure you can select some, of the banks, but I'm afraid you can't select all of them.
Well, I guess what I really want is after type legalization, but before operation legalization.
Oh, that's the thing. Here, there's no distinction between type legalization and operation legalization because there's no illegal type per se. There's only illegal operation. So you're just expanding or putting together operation. And there's not this notion of illegal type. Like if you have a very big type, what it means for your targets is just that it will be scattered through different registers, but we don't care. It's just a placeholder for a value. And what's really interesting is how you use it. And basically, it's just the operation that are illegal. But this is something you can play with a prototype. With your target-specific pipeline, you can try to put register bank select before if you think it's interesting for your target.
OK, let's thank the speaker.